All right, so hopefully you guys can see what's on there if I got that set up quite correctly. The other thing I want to talk about here first is I want to look at the homework. And I had a significant number of people not do the homework. Not huge numbers, but a significant number. And here's the problem with the homework in this class. Because I come in and I'm going to show you a solution, there's no late homework in this class. If you have a legitimate issue, email me if you're in the hospital. Let me know what's going on. We can come up with alternative assignments or something else. But this homework, once that due date hits, I put in a 0, it's done. So just be aware of that. So some classes, I know it's easy to do a late homework assignment. If you're using something like Connect and some of the other classes where it generates automatically stuff, this is a little different. But I want to go through it so you guys see where we're at. So the first piece I want to do is look at last week's homework. So this really was a couple of different things. We wanted you to get used to the idea of what pseudocode is. So it's an English language representation of our coding. So we're starting to kind of twist our brains to thinking in terms of steps. How do I break things down into algorithms? And so we wanted to look at how do I debug. So look at existing coding and try to figure out if there's an error in it. And then we had the idea of we want to start creating our own small coding. So the very first problem had a couple of different weird errors in it. So it says input midterm grade. And the dot really, yeah, you'll probably want to take that out. That's not really a huge issue, but it says midterm grade. Okay. Input final grade. And average equals input grade plus final divided by 3. And so there's several different issues with that. So we need to get rid of that dot. So we say, okay, that makes sense. Input midterm grade. Okay, midterm grade. Input final grade. Got it. But then this average, there's a couple of things wrong with that. So it says average equals input grade plus final. Is final the same as final grade? No. You have to be consistent in those variable names. And so we need to change that. Let me scroll down just a little bit on this page so we can see it a little better. I can get my cursor over there. So we need to be consistent in, so that average is equal to midterm grade plus final grade. And then up there it says divided by 3. Is that an accurate average if we divide 2 items by 3? No. So you're going to divide it by 2. And so I have something a little different. I put parentheses in there. Why would I need parentheses? So our computers follow that order of operations. Those things you learned in that 3rd grade, 4th grade, we learn about order of operations. So if I did not have those parentheses in here, so if I came in and I took out those parentheses, logically what this computer is going to do is it's going to come in here and says average is equal to midterm grade plus final grade divided by 2. It's actually going to take your final grade and divide it by 2 and then add it back to your midterm. Is that going to really give you an average? No. So you have to use those parentheses. So that's that idea of that logic error. Syntax-wise, the computer will read that and do that. It would say, yep, average equals midterm grade, and it would give you this average. So here we created a variable, and we said we're going to output that in some way. So those parentheses are going to be important. When you start looking at that, it's very easy because you know in your brain, hey, I wanted it to be this grade plus this grade plus this grade divided by however many. So we need to start thinking about how do I find those errors. So nothing in there is hideously tough. It's just kind of starting to think about how do those things work. So let me put those back in so you guys can see them. And so that is kind of my idea of a solution. Are there even better ways to do it? Yeah, we could do all kinds of things. But this takes that code and just cleans it up a little bit. And no matter what programming language we look at, if we have this structure, I can translate that into a programming language. And so that's why we work with this pseudocode. So a lot of times when we have a big project and we have coding requirements, we'll do this. We'll write the pseudocode, and then it gets handed off to a set of programmers who will look through it and then make corrections, changes. But if we handed this to a set of coders and we didn't have those parentheses in there, they may not know what an average is. So they would write it exactly the way we had it, and again, we're going to get a wrong response out of that one. So number 2, very similar, we had to look at how do I get the number of miles per gallon you get with your automobile? All right, so this one's just a really quick program. And the reality is a lot of this programming, when we talk about it, it's not done just for somebody on a computer. There are, in some cases, millions of lines of programming code inside of your car. So maybe this is the programming. It takes that input from something in your car and says, this is how many miles you drove, this is how many gallons of gas you used, and it puts that up on your screen and says, this is your miles per gallon. So input gallons traveled, or miles traveled, input gallons of gas used. So this one's got a couple of problems with it. So if I want to know how many miles per gallon, what does the per really stand for when I say miles per gallon? It's a divide symbol, miles per gallon. So it would be miles over gallon or miles divided by gallon. So miles per gallon really says what it is. And we have a problem here. We say gallons of gas used per miles traveled. Well, hopefully your car doesn't take more than a gallon of gas a mile. Is anybody's car that bad? No, hopefully not. So that actually needs to be reversed, and it needs to be miles traveled divided by gallons of gas used. Well, there's one more big problem in there. In the way we structure every computer language, that equals sign doesn't really mean two things are equal. When we look at things in the programming world, that equals really says is assigned to. And we always put the value, our variable, on the left. And so if I look down here, I've changed that around and I said, here's the value I'm assigning to, and this really says miles traveled divided by gallons of gas is assigned to the variable miles per gallon. And so that variable we're going to build is always on the left side. Always, always, always. I have not ran into a programming language that is not the case yet. It is possible that there is one, but I have not seen it. So we always put the variable we're going to assign values into on the left. That equals really says I am setting this value into miles per gallon. So in fact, when we start doing comparison operators, you're going to see that we use a little different symbol to say and ask that question, is this value equal to that value? Because we've taken over the equal sign and made it set up as a shoving it into that variable. So it's assigned to that variable. So the third one then, the third debug one, says we want to compute the cost per day and the cost per week on a vacation. Vacations are good. So here we have input the total dollars spent, input how long our trip was in days, and so now we have a variable cost per day. And we said, well, it's total money spent times days on trip. Well, what's wrong with that to start with? So what's wrong with total money spent times days on trip? Spencer? Nope, go ahead. It is a different variable. So the first problem is we've mixed up our variable names, and that's very easy to do. So it really needs to be total dollars spent. That's what we input. So total dollars spent. But if we want to know how much we spend per day, we don't take the number of days and how much we spent altogether. So imagine you went on vacation, you spent $500. You were on a vacation for a week. So your cost per day is $3,500 is what that's saying. Is that correct? No. So it's total dollars spent divided by the number of days. So cost per day, total dollars spent divided by days on the trip. And so there's a whole lot of other things in here. So we have weeks equal days on trip divided by 7. Well, that I can buy that. Does that make sense? That gives you a week, and it'd give you a decimal fraction. So if you spent 8 days, it would be 1.16 or whatever it would come out to. Got it. So I can agree with that. You scroll down a little bit, because it apparently is on the next page. So cost per week then, so we want to figure that out. We could figure that out because we have that weeks. We calculated it, so we could say total dollars spent divided by weeks, and that says how much per week we spent. And then we output a couple of things. That output means we send it either to the printer, we send it to the screen, whatever we do with it. So we output a couple of variables. So we output cost per day, and we output cost per week. Could we output how many weeks we're on trip? Yeah. We could do any of those values we have. We could output any of them. So that's just a really quick way to do that. So that's my solution. Up here is the pseudocode that's got some kind of error in it. So that's not the only way to have fixed it. You could do that with a lot of other ones. And so that was 9 points, 3 points for each one of those. The 11-point problem then, that's the one where we have a little more critical thinking in that we have to figure out an entire algorithm. You have to write that pseudocode down. So it may be helpful to write a flowchart so you can figure out what's going on. This one's pretty simple, but those flowcharts can help you when you start getting bigger or more complex problems. So this one says develop the logic that allows you to enter your hourly pay, the number of hours worked this pay period, and the percentage of gross salary that is withheld. Because you all remember back when you got your first job and you said, hey, I'm making $10 an hour, I'm going to have a check for $400, and then you got that slap in the face because taxes came out. That's what we're looking at. So it multiplies the gross pay by the withholding percentage, giving the withholding amount. Finally, it subtracts the withholding amount from the gross pay, giving the net pay after taxes. The program displays the net pay. Okay, so there are a lot of ways we could write this. So this is not the only solution. And I tried to look at them and see, did it make sense? So a couple of things I did in this one to kind of help out and start to organize. You're going to find that in almost every programming language, indenting is important. That indenting tells us that we have modules or that we have pieces that all run. So if you notice here, I put start and stop on the far left, and then I indented everything in here. So in here I said I'm going to input pay rate, number of hours, withholding percentage. So I got that from somewhere. That input doesn't necessarily mean that it came from somebody typing it in. It could be that this program is inputting that from QuickBooks, from another software, from a time clock system. Somehow we got pay rate, number of hours, and withholding percentage. So then I did this just to write it out a little differently, but let me sit down and type. It would be the same as if I said, so this is just to look at that logic. So I'm going to copy this line. So I'm going to tab over. So instead of saying compute, I could just say gross pay equals pay rate times the number of hours. And so now I'm saying exactly the same thing here. I could do the same with this line if I wanted to. In fact, I'll just get rid of this one. So withholding amount is equal to gross pay times percentage. And here I could say net pay then is equal to, or is assigned the value of gross pay minus withholding amount. So I built this now. We've got a really quick little algorithm. What's one problem with it? Is there a problem anywhere in there? Is there a problem in there? So, no. It's more of a logic issue just because of your knowledge of what happens at pay rate. Has anybody worked a job where you work more than 40 hours a week? What happens at 40 hours? You get, by federal law, at least in the United States, you get paid time and a half. So what I can do with these is I can run kind of in my brain or a desk audit. So I could come out here and I could say, okay, so that's $10. And number of hours would be, let's say, $40 or 40 hours. And our percentage withheld, so we'll just do it this way. We'll say 0.25 or 25%. We can do a desk audit on this and we can figure that out. So gross pay is equal to pay rate times number of hours. So that one's going to be equal to what? What is pay rate times number of hours? So 400 probably? All right, so what's our withholding amount then? So 0.25 times 400, or 100. And then our net pay should be 400 minus 100 equals 300. And then we output that $300. So you can do that kind of a throw in some numbers and look at it. So if we wanted to add in a way to check for over 40 hours, can we do that? Yeah. So let's write that really quickly or look at a way to do that. And we really haven't gotten all the way there yet, but I think our brains can process it. If we took in and we had a line and we just said number of hours, and notice they call this camel case. So the way we write that, because we don't want space in our variable names, but we capitalize every letter when we start a new word, that's called camel casing. So number of hours is equal to, and we could get really complicated, so number of hours. So how could we check and see if it's greater than 40? So we could do if statements. So we could say if number of hours is greater than 40, then we do something else, right? And we've kind of got our brain around that. So right now we know that this program, if you used it and you worked 60 hours, you're going to get ripped off, right? And if you work in the summer for a construction company, for example, 60 hours is a pretty short week in some cases. So these are the solutions I came up with for this particular set of problems. I want to come back. Make sure I'm in the right one. All right, so this week we start expanding that. So we've got some knowledge. We've already figured out a few things. So chapter 2, we start looking at some structures. So chapter 1, we really just used a little bit of our knowledge. We started the idea of that pseudocode. And so if I look at week 2, I have an assignment in here. And week 2 says, uh-oh, we have to do some other pieces. We have to design a game of some sort, and we'll look at that. But week 2, you need to read chapter 2, and we'll talk about some of the items in there. So the reality is we're going to tell you everything you need to know about a program today. All 3 pieces of a program are we're going to talk about today. And every program, whether it's Microsoft Word, whether it's Windows, whether it's Mac OS X, whether it's the programs run in the nuclear plant 25 miles from here, they all use these same basic structures. That's all they have in them. So it's a sequence, a selection, and a loop. That's it. If you can remember those 3 pieces, you can build any project in the world. 3 pieces. So it's like you have 3 different sizes and types of Legos. You can build anything in the world. And that's all we need to worry about. So we're going to talk about something called spaghetti code, which is not a good thing. We know spaghetti's good, but spaghetti and code are not good together. We're going to talk about this priming, and then we're going to look at structure. Why do we need structure? So, if we have code either logically snarled up or it looks really ungainly, we can't digest what's going on in a lot of cases. We call that spaghetti code. In other words, it looks like pieces of spaghetti running all over the screen. We don't know what is what, where it goes, how it operates, what it does. And generally, anything that looks like spaghetti code is going to be what we call unstructured. And so we're going to have some specific pieces for what we call structured. But the reality is, if it doesn't look logical in your brain, it's probably not structured. So structured means we only use these 3 pieces. And we can plug them in like Legos, but there's only 3 pieces. So, sequence, selection, and a loop. Sequence, selection, and a loop. That's all we can do. So, let's do the easiest one first. So, a sequence is what we just did our pseudocode on. It's a number of steps. There's no way that can branch. There's no way we can skip anything. Everything has to be done in order. And it's just a series of steps. Okay? So there are things in our life that are very much a sequence. There isn't a chance for us to branch off, change, or divest in any way. So a sequence then is those things we do in a specific order. Everything has to be done. So the one I always like to use is getting into the shower can be a sequence. We always do the same things to get into the shower. Because we know that we have to go to the shower, we have to get naked, and we have to turn on the water. If we don't do those steps in that order, we're not taking a shower. Right? If we skip the getting naked part, maybe you're doing your laundry at the same time as you're taking a shower. But it's anything we do in order. We can't skip any of them. And we're completing an entire sequence. Well, the programs we just wrote and looked at are a sequence. We had to do every step in those. So a selection asks a question. And we can take one of 2 paths. So here's where it gets a little interesting. Do we ever have things where we have more than 2 options? We do. But the computer, though, can really only ask yes or no questions. Remember, that computer can only think in zeros and ones. And so everything we do is based on that 0 and 1 idea. So no is 0, yes is 1, if you want to think about it that way. So everything we do, we can break down into those questions. Can I put multiples of those together to ask a question of 3 or 4 parts? Yes. But a single question can only answer one particular question. So, what we also call that, in a lot of cases, is an if-then-else structure. If-then-else. If condition A is true, then we do one side. If it's true, then we do the other side. So we ask questions. So if your pay is over 40 hours a week, we would go to the selection on the right. If it's not over 40 hours, then we're going to go to the selection on the left. And so that selection is one piece of this puzzle. We're going to plug those in. Because we're going to find we ask a lot of questions in our computer code. We ask things. So one of the things we do in this class with our textbook here is we build games. And we ask a lot of questions. So the last piece, we have just given you every piece. Sequence, selection, and now we're going to show you a loop. Because the most powerful thing our computer does is it can redo and go over things repeatedly over and over and over again in a loop. So, while something continues to remain true, we can continue to do this loop. So, think about a heater. Everybody in their house is grateful you have a heater right now. So, while the condition is true, so while the temperature is below 75 degrees, the heater continues to run. So we really combine, there we have a decision, and it's got to be a yes or no decision. So while the condition, so while it's 75 or below 75 degrees, we head to that yes, and in there can be any number of statements, but we say yes, the heater runs, and it comes back up to the top of the loop. It then asks that question again. Is the temperature below 75? Yes. As soon as that temperature hits 75, it's going to no longer be true, and then it drops out. That's how your thermostats work. You guys are all used to that idea. While people are still driving past me, I can't make a left turn, right? So while that's true, people are still going by, I can't turn until I get there. So what happens in that loop, what we make it do, so turn on the heat, turn left, drive, whatever, is called something that's in the loop body. We also have all kinds of names. So you'll call them loops, we'll call them repetition, you'll call it iterations. So this particular loop is generally called a while loop or a while do loop. There's different ways we can structure them, but this one is kind of the most basic and the most common one. A while loop. So that's it. Every program you are ever going to encounter has only those three parts. There's not really anything else. That's it. Everything you do has those three parts. From now until the end of the semester, if you decide to go on to programming languages and take 7 different languages at another school, you're only going to use these 3 parts. That's it. That's it. This is the whole key right here. Understanding those 3 pieces. Now what we can do with them, just like Legos though, is we can actually put these together. So the only way we can put them together is by putting them on from one end to another. And we'll show you why that's important here in just a second. So we need to put them, so a couple of end statements. So a lot of times we put end ifs. So we say that's where the decision end, we use an end while. So we want to be able to stack these together like modules, like Legos, stacking them up. And so here's an example of that idea. So now this doesn't really do a whole lot, but it shows we have a sequence. Now we have a selection. So we say, all right, we're going to do step A, step B. Is condition C true? No, it'll do step E. Yes, it does step D. That selection is done. That's its endpoint. And then we have a loop down here. And that loop says, while F is true, we do step G repeatedly. So we just go over and over and over again. As soon as that condition is false, we exit out. And that's it. That's how we stack those things together. Our three structures, we stacked them together. Think about it as having little endpoints, and we can just plug them in like Legos again. But we can get a little more complicated, and we can nest some of these things together. So when I say nest, we're putting one structure inside of another structure. And so the easiest one to look at is, I have a condition, and inside of that condition, I have now built a sequence. So condition and then a sequence inside of that. So we call this thing over here J, K, and L, that's steps. We'll a lot of times call that a block of statements. And so what you'll see in our pseudocode, and then when we actually do coding, you'll see most of the time those are indented, so to be at the same level, so we know that that's a block of statements that's going to execute all at the same time. We can also nest other things together. So notice on the outside we have our condition H. So we have a selection. We're saying, is condition H true or not? But notice here we have a sequence then. So we have a step, J. And then we have a loop. And then we have another sequence. So we can not only put them together in order, we can then nest that all inside of something else. So it can get a little more complicated. And if I look at my pseudocode up here, notice how I've indented that to show that. So the if statement, everything that happens inside of this if statement, so if condition H is true, is indented, right? And the step in, because that's inside of this loop, is indented one additional line. And so we can see where those come in. So those indentions start to get really, really important when we start breaking this out. So when I look at this, if I didn't have those indentions, I wouldn't know that those things are sitting inside of another one or nested inside of that. So we can get more complicated structures, but again, it's still using only those tools that we've had. So here, this one is kind of an elaboration on that. It's a little more complicated yet. So now, not only do we have a loop, but we put a condition then inside of the loop. And so if I look at my indentations there, so my outside loop is this if condition. If condition H is true, and notice it ends at the bottom. The next one is step J, and then my while. So while and end while, that moves over here. And then these two pieces, step Q or step P, are that farthest right indentation. Is that clear as mud? It takes some practice to write these and start thinking about it. But what we're trying to do is come up with ways we can utilize those three basic tools we have, and we can put them together. So let's talk about this idea of structure. So a structured program has only those three things: sequence, selection, and loop. That's all it can have. It doesn't mean that it has to have all three. Our programs that you debugged and you wrote for that payroll only were selections. That's all they were. And that could be a structured program. So it's got to have one or more of the structures. And they can only be connected to each other at their entry and their exit points. So in other words, that end while and that begin while. So thinking about those as having like little connection points, like Legos, little dots sticking up, that's how I wrap my head around it, is they can only nest together. So that's it. These three pieces. If you can arrange those, you're good for any programming language. You're good in this class. But it does lead to a couple of interesting, not necessarily problems, but a little bit more complicated issues. So this one is not structured. So let's look at it and look at why it's not structured. So this program has an issue or two. So let's think about this here and why it's an issue. So we say we start and we have our declarations. So we declare values. So a lot of times one of the things we'll do is we'll declare our variables and we'll do a housekeeping. So I've said original number, and it's a type of a variable called num. So we're going to call them a number. We have another number called calculated answer. A lot of times I like to just, for clearance, unless I know the values, I like to set them to 0. And I'll even do that right in that same step, just so it cleans up. And it says, all right, input original number. And then we're asking EOF. EOF says end of file. And so this particular program says, as long as I don't type in something like 999, a key value, it's going to continue to run. So as long as I don't type in something that tells it to end, it's going to continue to run. So EOF is just our shortcut for saying end of file. So end of file says, if we hit that value, we're going to stop the program. If not, it's going to take its original number, multiply it by 2, and output that as calculated answer. So you look at that, that seems logical, doesn't it? So why is that not structured? Has anybody caught why? What the issue is with that? What is the big issue with this program? It looks like it would run logically, doesn't it? So, is this a sequence right here where we have an input original number? Is that part of a sequence? Or is it a sequence? And where did I say each piece of these? So here we have a decision, right? Where does this decision have to return to? It's got to return right to the top of that decision. It can't go back up here and go into the top of this. This, to be a structured program, this has to come right back up to the top of itself. So if I do that, if I come back up to the top of itself, let's think what happens. So we've changed this, so now instead of coming over there, it's going to come up to the top of the end of file. Is it ever going to then get a new number? No. And so that's kind of an issue we have with these. And so we have something called a priming value that we need to do. So this particular program, this is that program rewritten to be structured with that same code. And so now we declare our numbers, we input the original number. So we input 12. Comes down here. Our values to get out of this program were 999. So it says nope. And it's going to output 12 times 2 is 24. It's going to output that. What's it going to do forever? Is that program just going to loop and shove 12s on our screen forever? Yeah. So the program is structured, but so we rewrote it. So it is a structured program, but it has a logical error, doesn't it? You've created what we call an infinite loop. Once I put in that original number, there's no way to get another number in there. And so this is going to run forever and just spit out whatever values we had originally. There's no way for it to get an additional value. So we need to fix that. So we want it structured and we want the program to work. So what we have to do in most cases when we get an input and we ask a question, we call it priming inputs. So it seems like we're duplicating our work, doesn't it? It really does, but this keeps our program structured and it allows this program to work. So what's the difference? So this looks very similar, except in this sequence, we add that input original number. So when you look at it, it says, why do I have two of those? Well, this first one is a priming input that says, all right, that's our priming the pump or shoving it in to start with. Then we have a value that gets asked again. So after it multiplies it, then it asks for another number. That doesn't violate anything. It comes back up. And if we typed in 999, it would then stop. Or any other value, it would continue that loop. So this is the hardest thing to wrap your heads around, I think, in here, is that idea of that priming input. And if we use structured code, that's what we have to do. So you'll end up with, in this case, two inputs. So one gets run once. That second input could run 1,000,000 times. It could run once, right? And in fact, if you, at the original input at the very top one, put in that what we call a sentinel value, or 999 in this case we said it was, this one would never run because it would immediately X out of that loop in that program. So that is probably the most complicated piece we have. So why do we want to do that this structured way? Well, it's kind of our accepted structure. So the biggest piece is this idea here of modularity. So if we all write with the same structure and the same coding expectations, whether it's in pseudocode or in actual code, in a language, that gives us that what we call modularity. I can take a module and take it from one place and plug it into another. So picture Toyota. Does Toyota make a lot of different cars? They like the idea of modularity because I can take the same brake part and I can put it on 5 different Toyota models, right? We use those same modules over and over again. Well, Toyota also does it in their coding because each car module, they use the same code, and think about that module for miles per gallon. I can reuse that code chunk because it's a module, and I can plug it into a Camry or a Corolla or a Prius or a Toyota Highlander, and I can do the same thing. So it's good for that reason. That's really kind of the best one. But the other reason, this idea of professionalism, because most programs aren't written by a single person. So when I think of Macintosh OS X, that wasn't one person that wrote that whole thing, was it? And in fact, Apple has an idea that there is a limit to the size of programmers that you want in a pool, and they think about 100 is the maximum number. So there's probably 100 people coding, or maybe more, or 100 teams at least, working on Mac OS X. If we all picked our own ways to write stuff, would that be ugly when they tried to put it together? Yeah. And you may not be the person to look at this code 10 years from now. Hopefully the code you write outlasts you. And in fact, we're running into that issue right now. Banks want people who can code in some older languages because they have programs that are still running from the 1960s, and they're trying to figure out how can I look at it and add pieces, and they need that idea for maintenance. So your code may change, and so we have to come up with a way to maintain it in the future. So we have that idea of maintenance. Maintenance is really, really important. Even for the fact of your own code, you're working on a project, you're working on a program, you come back to it a week later. Well, this made sense in my brain earlier, but no, I can't remember what I was doing. But if we have this idea of structure, and we have this in our head, it makes life a little easier. So I'm going to jump through this. And I want to look at a little bigger program before we jump into anything else. So I want to look at a dog washing program. Has anybody washed a dog? Yeah, it's a process. Has anybody tried to wash a cat? No. It's an even bigger process. So this is, and let me move my mouse up here so you guys can see where I'm at. And on the recording, it should have a big blue thing or something, I think, if I remember right. So we have a start and we have a stop. And I almost always start out my flowcharts with that. I put a start symbol up at the top and a stop symbol at the bottom. That way I know everything I do is going to be contained inside of there. Same way with my pseudocode. I have a start and I have a stop. And the great thing about some of these text programs is I can add lines in there. If I'm writing on a notebook, it's a little hard to add extra lines, but I can start and stop each process. So I'm going to start, and we know that the first thing we're going to have to do is we're going to have to catch the darn dog. And if your dog has had a bath before and they see the word bath, what are they going to do? And you say, hey, Fido, come here, let's get a bath. Immediately they run away. Crap. And so the first question we ask is, does the dog run away? If yes, we have to catch the dog. And so we reiterate that loop. Until we or the dog gets tired and this program ends, right? So your dog finally, after about the 7th time you catch him, gives up. The dog doesn't run away, so now that answer is no. The dog didn't run away, so we turn on the water. Well, when we turn on that water, what does the dog immediately do? I'm going to run away. So then we have to ask the question again. Does the dog run away? If the dog does, well, crap, we don't know how long it's going to take to get him. We move into that sequence of turn off the water, catch the dog, and then notice that this module, really it's kind of similar to up there, except now we've added the turn on and turn off water in there, right? Because we don't want to leave the water running. We want to be ecologically friendly. So until the dog doesn't run away again, we're going to repeat this loop, turning on the water, catching the dog. The dog finally said, I'm going to stay still. We get the dog wet. We put shampoo on him. Generally, that's when the dog jumps out of the bathtub and runs away again, right? So, again, we have a does the dog run away? If yes, we turn off the water, catch the dog. Does the dog run away? And notice that this piece is identical to that module up there, isn't it? Yeah. And so, once the dog decides he's not going to run away, then we can rinse off the dog and we're going to stop. So, could we have added another module of blow drying the dog to get him clean and dry? Yeah. And again, yet another piece in there. So, if I look at my pseudocode for it then, so our start and our stop are all the way at the left. And so here we have the catch the dog. While the dog runs away, you're going to catch the dog again. So if the dog takes off, we have to go catch him, right? Nowhere in here is there shooting the dog because you're now irritated at him, right? Okay, just checking. That would be a whole different set of code. So here we have the while loop. While dog runs away, we turn off the water. Notice here this piece, catch the dog. While dog runs away. So these two are identical modules. So once I created that, I get to reuse it. So we have to come up with some structure. If we're asking questions where we have an input, we have that idea of that priming the pump input. So this is everything you need to know about programming in week 2. So each structure, we can use any of those 3. We can combine them in interesting ways. Structures can be nested or stacked. So I can put things inside of each other, but they still have to be able to be taken out in blocks. Being able to look at that structure and work your way through that flowchart, work your way through that pseudocode to make sure that it logically works. So, for example, this dog washing one, I would go through and pretend you're the dog. Make sure that logic works, and make sure you can take this flowchart and translate it into the pseudocode, vice versa, and understand why that works. So this chapter is a little interesting in that we're trying to get you to introduce new ways of thinking. So one of the things I want to introduce you to, Word is a great word processing program. Word is a really bad tool to try to code anything in, whether it's pseudocode or when we get to Python and we start doing it. So I want to introduce you to a friend of ours, a program called Notepad. anybody used Notepad before? No. Some of you maybe. So Notepad has the advantage of outputting just a text file. Very short, very simple, very easy. It doesn't add all the overhead that Word does. And that's one of the things we want. So if you click on your Windows icon and you start typing, and of course it's going to show up in the monitor that you don't see. I'm going to type Notepad. And on your computers in the lab, it's going to automatically pop up a program called Notepad++. We will show you that program, but it also has one just called Notepad. And I'm going to open it. There is nothing to that, is there? That's as plain as it can get. There is one change I would encourage you to make just to make life easier for yourself. So where it says Format, I would have you turn on Word Wrap. Just so if I reach the end of the line, it'll wrap to the other bottom. This is what I'm going to encourage you to do your homework in when you're just doing the pseudocode. It has the copy and paste, so I can do Control-C, Control-V, but it's very easy to put in code. So I could have a start, I could have a stop. It doesn't have all the other pieces in there. So while dog runs away. And notice I have the tabs and I can and what it saves as, if I go to File, Save, and of course I want to do the Save As so I know where I'm going to save it, it saves these as TXT files. They're short, simple, lightweight, easy to upload. So one of the issues I had with several people is they're using Google Docs or they're using a program on a Macintosh. If we save it as a TXT file, just a simple text file, it's small, it's easy to upload, and I can grab those right away. It doesn't add any extra weird formatting. And in a lot of cases, we can actually create a program. In fact, our first programs in Python, we're going to write right in the Notepad app. It's that simple. So this is kind of a universal way we can store data in this called Notepad. So if you haven't used Notepad, I encourage you to try it. It's a great way to write things like this coding. Notepad++ is another great tool, but it's got a little bit of a learning curve, and so we'll introduce that as we go through here. So your assignment then, I'm going to encourage you that you can do most of it in Notepad, and then you turn in this TXT file. Very simple, very short, very easy to do. Let me get this out of the way, maybe if it'll move. So this week's assignment, so a set of questions, and we're taking them right out of the class, out of the back of the book. And remember that book is available in week 1, that PDF file. So chapter 2 says, here's our question. You only need to do one of these items. So we're going to draw a structured flowchart. A retail store employee should follow to process a customer purchase, include at least 2 decisions. So while it says you can do a flowchart or a pseudocode for any of these, I'm going to encourage you to actually do both pieces. So that flowchart, on Thursday I will show you some tools to create those on the computer. But quite frankly, you can sit down and draw those flowcharts out also and think about them. So we have a couple of things. You can do a children's game, you can do a television game show, or you can do a professional sport. How do the rules apply? Now, I will say that some of those can get kind of complicated, so we'll shortcut those a little bit. You're not going to have every rule in football, for example, or baseball in there, but you can get a general idea of the game and then keep adding pieces in there. So on Thursday, we're going to work on that homework. For those of you that are on campus, we're going to work on it in class a little bit, You will not get it done in class. I have not had very many students ever able to do that. But it is good to start. It's a practice, writing down that idea. So now I know how the three pieces work. How do I start communicating those together? So, any questions about the homework? Any questions about the assignment? Yes, sir. It is 20. All right, so the first three questions were worth 3 points apiece, or 9 points. The last question was worth 11 points. So altogether, it was worth 20 points. So if you got a couple points off, that means you missed a couple pieces in the debug. If you skipped a section, it's really hard to get grading on that. So, and that's what some people did. They did the 3 debugging things. I had some people do only the last 11-point question. So I'm not really sure on there. So there is a test off of Chapter 2 also. So don't forget about that. I think I only had a couple people that managed to not do the test. But remember that book then, for this particular beginning of the class, is this PDF right here in week 1. And so once you've downloaded it, that is the textbook. I didn't want to have to make you buy more textbooks. This one, we haven't changed a lot of our structure. So understanding structure here, we're going to go back into making decisions, loops, so you can kind of look ahead and see what we're doing. So you can download that and read that on any device, or you can obviously get it inside of Blackboard. And if you click on that link there, it'll open up in its own link, and it's probably a little easier to read. All right. Any other questions on the homework? No. It takes a little bit to get used to what we're doing in here. So I appreciate everybody's work on that.